proton will occur inside the nucleus. So first we'll take the beta decay. Just wait some. Okay, first we'll start with the beta minus decay. What happens in this? So suppose it is a parent nuclei. Parent nucleus. So in this case, what will happen? From the nucleus, what will happen? Inside the nucleus. Inside the nucleus. So what you should do is one of the neutron will get converted into, well, I'll write it here. Neutron will get converted into proton. Neutron will get converted into proton and will get one electron and then anti-neutrino. Neutron, proton. That electron is called as beta particle, beta minus, and this is anti-neutrino. So inside the nucleus, so what happened? The mass number, the mass number remains same. What happened? Atomic number will increase by 1. And as it what we get one beta particle, beta minus plus anti-neutrino. Where do this occur? Inside the nucleus. There's everything occurs inside the nucleus. I'll put it, this will be, means sir, inside the nucleus, neutron can get converted into proton. Basically, what is a neutron? Neutron is not an elementary particle. It's not a fundamental particle, no. It is inspired, like it is inside what happened, it's made up of quarks. So of course, all these are not there for syllabus. Just have an idea that. So inside that, what happened, the nucleus, the neutron, what happened, is made up of quarks. And what it will do, it will up quark and down quark will be there. Like this, and constant what happen, these quarks what happen, they'll exchange energy. That we'll call as muon. This is called like a quark. So it is basically that one. Using electron scattering weapon, we are able to find out, we are going to go inside the neutron. Inside again, neutron is made up of quarks, up quark and 2 up quark and 1 down quark. Not there for syllabus, so I don't want to pressurize you anything. Nobody will ask you. Just have an idea that one. These neutrons what happen? Outside the nucleus, they are unstable. What is the lifetime of neutron outside the nucleus? Around 14.3 minutes. The lifespan of neutrons, of free neutron. I'm saying free neutron. What do you mean by free neutron? One which will be outside. Free neutron is 14.86 minutes. Some books they're telling for 14.32, approximate it is. There's the average lifespan. Average lifespan of free neutron is 14.8. It's not a stable. So what will happen? If the free neutron, what will happen? Will undergo same thing, like, because the mass of the neutron is greater than that of proton. So then the neutron will become a proton. Then what happen? Will get electron emitted from it and anti-neutrino. No, we are not bothered about this free neutron. We are bothered about the stability. So what happens is, there are some nucleus are there where if it can decrease one neutron and increases one proton, it will jump into stability curve, you know. This is what happens, you can see. The nucleus 2, it decreases one neutron. At the same time, what happens? It will increase one proton here, Z plus 1, by beta minus decay. It will enter into stability. Not only this, even the uranium will undergo beta decay. This I'm just giving classical example here, that's all. All the radioactive substances will undergo beta decay, not only one, two. All radioactive substances will undergo alpha, beta plus, beta minus decay. No, basically neutron orbital is unstable, free neutron. Then how come neutron inside the nucleus is stable? Yes, there also what happen? It is unstable. What it to do? It will exchange the muons with the protons. Again, the protons open. Proton outside the nucleus they are stable. Proton outside the nucleus is stable. Inside the nucleus, proton is not stable. So not stable means what they do? It will exchange energy from the. So when the neutron what happen? Like gives energy to the proton will become neutron. I think I'm just simple because again it's a very wide topic. We need around some 6 hours to go into the nucleus. Not possible. So they will exchange this one. This neutron is unstable, no? So what it will do? It will give out energy to the proton, and it will become this neutron will become a proton after giving out. This proton after gaining energy has become neutron. So like that. The constant what happen, there'll be exchange of energy between the neutrons and protons, and what happen, they'll not undergo decay. Free proton is you bring proton, keep it outside, it is stable, no problem. But inside the nucleus it's not stable. To attain stability, what it will do, it will also be exchanging energy, and to exchange that energy what is needed, there should be higher quantum state, because what is the energy of neutron more than proton, no? So there should be some lower state should be available. So like that happen inside the nucleus, constant. They are not happy, neutron, proton. They're struggling in their own way to survive. Because quantum states will be there. For the neutron to become proton, what happen? There should be lower quantum state should be available. No? This is higher quantum state, lower quantum state. Similarly, proton to become neutron, higher quantum state should be available. So like that what happen? Then proton itself, what happen, will become neutron, neutron, proton by exchange of the quarks, what we say. And again, what happen? Inside the neutron, this condition will arise. So I'll not touch this topic. It's a very wide, we have to go in depth, with not part of syllabus here. So fine. So now what is the reason is, now what we can say is like, inside, now why do the neutron will become proton? It's not because of, since neutron is unstable to become stable proton. No, the atom, the nucleus itself is unstable. To attain stability, what happen? If it can increase its atomic number by 1, it can attain stability. For that purpose, what happen? The neutron inside the nucleus can become proton. Means now you have to ask one very beautiful question. Sir, okay, unstable nucleus, to attain stability, neutron will get converted into proton inside the nucleus. Okay, fine. Those nucleus which are stable, will there be any conversion? Yes, there must be conversion, because basically what is the nature of neutron is unstable. To attain stability, it has to get converted to proton. Like that, the mutual conversion between neutron, proton will be occurring all the time. This is for stability for what? This particular equation I wrote, stability for neutron or stability for nucleus? Stability for the nucleus. Getting the idea? So don't get carried away now. Don't think that only in radioactive substance the neutron proton conversion takes place. No. I think maybe in chemistry you're going to study, but as far as physics what happens, let's not confine. Because again we have to enter into particle physics, nothing to do that one. So first particle physics, some 10-15 hours we have to study only particle physics. Then we have to enter into all this one. So we have just removed all that, only like a story we are, I'm telling you, just accept it. So whether irrespective of whether the nucleus stable, unstable, so there will be a conversion of from neutron to proton will be occurring all the time. This is for to have the stability of the nucleus is what this conversion is occurring. Got the idea? Okay, let's write now. What will happen to why this anti-neutrino is brought? So when we study the to bring the to conserve kinetic energy, to conserve the momentum, to conserve the angular momentum, this anti-neutrino is brought here, and it will very weakly interacts with matter. Very weakly interacts with matter means after some covering a distance of say around say like a 13 kilometer in the concrete wall, then the anti-neutrino what will interact with the matter. In the 70s, 60s, what happened, this is what happened. Now later on, with technology got improved, we are able to trace it out very easily. Measurement of its, it weakly interacts with matter. That much I can say here. Why it is brought? To conserve the momentum, to conserve angular momentum, to conserve the kinetic energy, to conserve even the spin also. This anti-Newton is brought here. Now let's write the basic equations. Now, what about the energy released? So what all initial energy will calculate? Ui. Initial energy, it will be mass of dot nucleus minus mass of what is UF? Plus 1. Why do this ME? This is the, so what you should say? This is the beta particle, no? Write it here. Beta emitted beta particle. What is the mass of antineutrino? Negligible. It is very feebly interacts with matter. Almost the mass is negligible. You can put it. It is don't call again radiation. Mass of that is carried by it is mass of that rest mass. You can put it 0, but don't call photon. Antineutrino don't call photon. Okay, this is about the energy equation. So let me go for. So finally, how much this will end up? Mx z plus 1 a minus me plus me. I think this will agree. This is for that daughter nucleus. Okay, let it be like this only. X only. This is the parent, this is the daughter nucleus formed. So this will become, so now the Q is what? Ui minus Uf. So how much will get it? This what happens. This what the energy is. This energy who will carry? Kinetic energy of the parent formed, daughter formed, plus kinetic energy of beta minus kinetic energy of antineutrino. This will be negligible. Huh? You look at the mass of beta particle and the mass of the daughter formed will be negligible. So finally what happened? We can put it approximately K beta, this one. Next again, I'll take the active beta minus decay sample. Like that, the some 110 atoms, I'll take it, 10 atoms of X, they'll undergo beta minus decay. What will be the kinetic energy of all beta particles emitted? Different beta particles will have different energy. The reason for that, what all that available kinetic energy will be shared between beta particle and antineutrino. Will be shared between beta particle and antineutrino. So when I plot the graph, Z plus M, that will be the mass of charge of atom form will be what happened? Neutral, no? It should be.
So number of electrons around the atom will be Z only, before and after.
O side.
From where will an extra electron come, sir?
That's what, no? The energy equation that will be created, no? Now this will be kinetic energy of beta minus number of beta particles. This will be. If you look at this, so, this is what the something K max. All the emitted beta particles need not to have that one. So most of the particles I'm saying that one, like a active beta minus decay. Active beta minus decay means say some around in 10 gram. Definitely there'll be millions of the beta decay particles. I'll get it. When I measure, no, there are some like most of the beta particles. They'll have their most of the beta particles. They'll possess one energy, and that is not equal to K max here. And look at this particular beta particle, which is possessing maximum kinetic energy. What should happen to energy of the antineutrino will be negligible. What about this? There are some beta particles which have very less energy. Some books they have connected to this, and some books they have left some gap. I think it's justified. In Singage or other book, what when they have connected it, so you can just leave a gap. So zero kinetic energy, how it is possible. So leave some small gap. We'll start like this. So you look at this one. There are some set of beta particles are there where they're having less kinetic energy. Then who will carry the remaining energy? By the antineutrino. So like that, what all that energy available will be shared between Kmax and antineutrino, and they're not in some any proportion, like not like alpha particle and daughter nuclei. So is it all beta particles will have same energy? No, the different beta particles will have different kinetic energy in active beta decay sample. So what is this meaning of this graph? I think okay, we'll keep it here. Different beta minus particles will have different kinetic energy. Will not be monoenergetic, no? Shall I put monoenergetic? Alpha particles are monoenergetic. What about beta particles? Will not be monoenergetic. I think this was the equations given in most of the best modern physics book and even in SC Verma. I just picked up. Chances are there asking of this kind for also you. Tell me like what is this? What is the interpretation of this? Mass of, is it a daughter, is it a parent nucleus or mass of the parent atom? Mass of the parent atom, mass of parent atom minus valence electrons will be the, is what it will come now. So this what, not mass of the parent nucleus, mass of the parent atom, mass of the daughter atom formed. I wrote, I written this one, atom minus that one, that will become nucleus, no? So this is what we interpret like this here. Now, anti-neutrino, let's not bother much. Our syllabus will not help us to go into much in depth all. So how the anti-neutrino will come, all that one. So just like a story, you can put it. Of all this statement is very important. The different particles will have different kinetic energy, and there's a particular graph you can put it. So why that anti-neutrino is brought? Anti-neutrino, why it is brought? Anti-neutrino. Without antineutrino, what will happen? Angular momentum, and the kinetic energy will not be conserved. To conserve angular momentum, linear momentum, and also the angular momentum and spin, this antineutrino is brought into the picture. And it will weakly interact with matter. These are some theoretical questions they can ask you. No, it happens that the daughter nucleus formed will not be in what, like will not be in a ground state, this one. So in that case, what you should do, then it will give out gamma photon. In that case, what you should do in Q, what all that energy available will not be shared by this one. Even gamma photon also will come. I think you have this question in SC Verma. After beta decay, if the particular daughter nucleus formed, if it is not in a ground state, then it will undergo de-excitation, will give out gamma photon. In that case, what all that energy available due to mass defect, that should be even shared by the gamma photon. We'll go for next beta minus O, no? Beta plus will go for it. Inside the nucleus, a reaction will occur where a proton gets converted to neutron, then we'll get positron and a neutrino. So there's a proton. From where this positron and neutrino will come? From where it will come? From the nucleus. It will be. What should be the basic reaction? X, Z, A. Proton, so this will be, shall we put Z minus 1? Number of nucleons will remain same. And this is beta plus and neutrino. Okay, let's write the energy equation in this case. Ui is equal to UF equal to. Now what should happen to, if the charge of nucleus decreases, then the charge of, we should write like this, plus, this is Me into C square. So this is what is this? This is the positron, mass of emitted positron. See, I suggest you, instead of trying to read a higher level of nuclear physics, the more best questions are asked here. So what will happen to the emitted positron? It will move in a magnetic field, then it will be accelerated by electric field. And this positron, what happen? I'll accelerate it. I'll go and make it to strike the target. Then we'll get X-rays. Please, this is very important. So I suggest you, like, don't get carried away by reading higher theoretical things. No use. Nobody will ask you anything of that one. Somebody asked particle physics, that one. Definitely, if you are writing some any competitive exams for Tata Institute of Fundamental Research only, it will help, or BARC. So when you go for any interviews in that particle physics notes will help you. Otherwise, for our mains advanced, no use. Or when you go for Olympiad, that will help you. Otherwise, our mains advanced, what all I sent it, no, it's of no use. Huh? So don't get carried away that if you know higher things, you can manage better. Nothing to do. Instead, our questions will be like this. Huh? This emitted beta particle, I'll make it to pass through magnetic field, electric field. I'll accelerate it. I'll go and make it to strike the target. Then X-rays will come. All applications. So focus more numericals of that kind. Huh? Don't just involve in reading theoretical ideas. No use. So let Q is equal to Ui. Okay, before that we'll solve this. Mx z minus z me. Look at the calculation part. No, we'll go for Ui minus Uf. Why Ui minus Uf? Because I have mass information. No? When energy will be released, when mass of parent more than that of daughter. No, strictly, what is this? Mass of the parent atom, mass of the daughter atom, mass of the valence, mass of the electron. No, like whether the beta plus will occur or not will determine. Means how to decide this, which reaction will occur. Means suppose say they give reaction, they'll ask us to check whether alpha, beta plus or beta minus. Who will determine that? Whether the reaction will take place or not, how to judge it? You calculate Q. If Q positive, reaction occurs. Q negative, reaction will not take place. You you are going to get questions of these in advance. So they are going to test you whether you know how to calculate Q or not. So I'm repeating once again. If you get Q negative, reaction not possible. If you get Q positive, reaction is possible. In numericals, what is the technique? Whether reaction occurs or not, whether given beta decay process or not. If Q positive, reaction occurs. Q negative, reaction will not occur. So they'll check you that one. They'll give some all, everything. And there is a whether possible beta decay process undergoes or not. You directly come and calculate Q. Positive means as it occurs, negative means will not occur. If there's a positive, then I'll ask you further what is the kinetic energy. So what all the kinetic energy here will be? Kinetic energy of the positron plus kinetic energy of the neutrino. If the daughter nucleus formed is in excited state, what do we get? So we have to go for kinetic energy of the gamma photon. So we do have very few problems. If you take some SC Verma available, some around 2 are there in Singage, there are around 3 are there. That all related to this one only. Possible or not. Like earlier, how we did alpha decay, no? The similar method you have to apply here. So I'll focus problems tomorrow. Let me introduce to the fission, nuclear fission. So at least some theory will finish off. So tomorrow we can focus totally on numericals. Here, what about all beta particles will have same kinetic energy? No. The what all kinetic energy will be shared by K gamma, this one, neutrino and positron. Will it be monoenergetic? No. Different beta particles will have different kinetic energies. So different beta plus particles will have different energy. What all available energy will be shared by both. Okay, now we'll enter into the fission concept. At least theory, half an hour there, no? We'll finish off theory. So nuclear before that, binding energy